In this video, we'll explain what SQL injection is, describe some common vulnerabilities, explain how to find and exploit SQL injection, and summarize ways to prevent the vulnerability from happening. SQL injection is a web security vulnerability that allows an attacker to interfere with the queries that an application makes to its database. It generally allows an attacker to view data that they are not normally able to retrieve. This might include data belonging to other users, or any other data that the application itself is able to access. In many cases, an attacker can modify or delete this data, causing persistent changes to the application's content or behavior. In some situations, an attacker can escalate an SQL injection attack to compromise the underlying server or other back-end infrastructure, or perform a denial of service attack. Consider a shopping application that displays products in different categories. When the user clicks on the gifts category, their browser requests this URL. This causes the application to make an SQL query to retrieve details of the relevant products from the database. This SQL query asks the database to return all details from the products table where the category is gifts and released is 1. The restriction that released is 1 is being used to hide products that are not released. For unreleased products, presumably released is 0. The application doesn't implement any defenses against SQL injection attacks, so an attacker can construct an attack like this, which results in this SQL query. The key thing here is that the double dash sequence is a comment indicator in SQL, and means that the rest of the query is interpreted as a comment. This effectively removes the remainder of the query, meaning that all products are displayed, including unreleased products. Going further, the attacker can cause the application to display all the products in any category, including categories they don't know about. To do this, the attacker can send this attack, which results in this SQL query. The modified query will return all items where either the category is gifts or 1 is equal to 1. Since 1 equals 1 is always true, the query will return all items. Consider an application that lets users log in with a username and password. If a user submits the username Wiener and the password Blue Cheese, the application checks the credentials by performing this SQL query. If the query returns the details of a user, then the login is successful. If not, then the login is rejected. In this situation, an attacker can log in as any user without a password simply by using the SQL comment sequence to remove the password check from the where clause of the query. If the attacker submits the username administrator quote dash dash, then the application performs this SQL query. This query returns the user whose username is administrator and successfully logs the attacker in as that user. In cases where the results of an SQL query are returned within the application's responses, an attacker can leverage an SQL injection vulnerability to retrieve data from other tables within the database. This is done using the union keyword, which lets you execute an additional select query and append the results to the original query. If an application executes this query containing the user input gifts, then an attacker can submit this input. This will cause the application to return all usernames and passwords along with the names and descriptions of products. When you've discovered an SQL injection vulnerability, it's generally useful to obtain some information about the database itself. This information can often pave the way for further exploitation. You can query the version details for the database. The way that this is done depends on the database type, so you can infer the database type from whichever technique works. For example, on Oracle, you can execute this query to show the database version. You can also determine what database tables exist and which columns they contain. For example, on most databases, you can execute this query to list the tables in the database. Many instances of SQL injections are blind vulnerabilities. This means that the application does not return the results of the SQL query or the details of any database errors within its responses. Blind vulnerabilities can still be exploited to access unauthorized data, but the techniques involved are generally more complicated and difficult to perform. Depending on the nature of the vulnerability and the database involved, a variety of techniques can be used to exploit blind SQL injection vulnerabilities. You can change the logic of the query to trigger a detectable difference in the application's response depending on the truth of a single condition. This might involve injecting a new condition into some Boolean logic, or conditionally triggering an error such as a divide by 0. You can conditionally trigger a time delay in the processing of the query, allowing you to infer the truth of the condition based on the time that the application takes to respond. You can also trigger an out-of-band network interaction. This technique is extremely powerful and works in situations where the other techniques do not. Often, you can directly exfiltrate data via the out-of-band channel, for example, by placing the data into a DNS lookup for a domain that you control. The majority of SQL injection vulnerabilities can be found quickly and reliably using Burp Suite's Web Vulnerability Scanner. You can find SQL injection vulnerabilities manually by using a systematic set of tests against every entry point in the application. You can submit the single quote character and look for errors or other anomalies. You can submit some SQL-specific syntax and look for systematic differences in the resulting application responses. You can submit Boolean conditions and look for differences in the application's responses. You can submit payloads designed to trigger time delays and look for differences in the time taken to respond. And you can submit payloads designed to trigger an out-of-band network interaction and monitor for any resulting interactions. Most SQL injection vulnerabilities arise within the where clause of a select query. This type of SQL injection is generally well understood by experienced testers, but SQL injection vulnerabilities can in principle occur at any location within the query and within different query types. The most common other locations where SQL injection arises are in update statements within the updated values or the where clause, in insert statements within the inserted values, in select statements within the table or column name, and in select statements within the order by clause. First-order SQL injection arises where the application takes the user input from an HTTP request and in the course of processing that request, incorporates the input into an SQL query in an unsafe way. In second-order SQL injection, also known as stored SQL injection, the application takes user input from an HTTP request and stores it for future use. This is usually done by placing the input into a database, but no vulnerability arises at the point where the data is stored. Later, when handling a different HTTP request, the application retrieves the stored data and incorporates it into an SQL query in an unsafe way. Second-order SQL injection often arises in situations where developers are aware of SQL injection vulnerabilities and so safely handle the initial placement of the input into the database. When the data is later processed, it is deemed to be safe, since it was previously placed into the database safely. At this point, the data is handled in an unsafe way, because the developer wrongly deems it to be trusted. Some core features of the SQL language are implemented in the same way across popular database platforms, and so many ways of detecting and exploiting SQL injection vulnerabilities work identically on different types of database. However, there are also many differences between common databases. These mean that some techniques for detecting and exploiting SQL injection work differently on different platforms. Differences between databases arise in areas like syntax for string concatenation, comments, batched or stacked queries, platform-specific APIs, and error messages. Most instances of SQL injection can be prevented by using parameterized queries instead of string concatenation within the query. This code is vulnerable to SQL injection because the user input is concatenated directly into the query. The code can be easily rewritten in a way that prevents the user input from interfering with the query structure. Parameterized queries can be used for any situation where untrusted input appears as data within the query, including the where clause and values in an insert or update statement. They can't be used to handle untrusted input in other parts of the query, such as table or column names or the order by clause. Application functionality that places untrusted data into those parts of the query will need to take a different approach, such as whitelisting permitted input values or using different logic to deliver the required behavior. For a parameterized query to be effective in preventing SQL injection, the string that is used in the query must always be a hard-coded constant and must never contain any variable data from any origin. Don't be tempted to decide case by case whether an item of data is trusted. It is all too easy to make mistakes about the possible origin of data, or for changes in other code to violate assumptions about what data is tainted.